So up till now, we've been looking at chemical reactions so that we could figure out what the reactants are, what the products would be. And we haven't really talked too much about the how much of these reactions. And the whole purpose of stoichiometry, and that's the word that you see up here, stoichiometry, which means element and measure. Metry means measure. The whole purpose of that is to actually measure amounts of reactants, amounts of products. What if you have this much reactant, how much product will you get? If you got this much product, how much reactant would you have had? So again, we're talking about amounts that are used in and produced in chemical reactions. In stoichiometry, you need a recipe. It's just like any other cookbook work. Stoichiometry really is cookbook. How much of the ingredients you need, how much of the products you'll end up with, because that's an important point here. And for stoichiometry, the recipe comes from a balanced chemical equation. That's why we spend so much time at both writing equations and balancing them, because that's going to be the key to doing accurate stoichiometry. For a general equation like this, when we say we want to balance an equation, and what we're looking at is the coefficients of each of these substances, both the reactants and the products. So remember that each of these numbers represents number of moles. So I have 2 moles of A, 3 moles of B, and 1 mole of C. The amount that we're going to be using and the conversion factor that we're going to be using in stoichiometry is called the mole ratio. Sometimes it's called a molar ratio. Both of those things mean the same thing. And the molar ratio come from the coefficients of that balanced reaction. So in the example that I've given here, which is nitrogen and hydrogen making ammonia, when it's balanced, I have 1 mole of nitrogen plus 3 moles of hydrogen produce 2 moles of ammonia. These are the ratio, or these are the coefficients, or the mole numbers that we're going to be using for the mole ratio. Remember that just because you don't see a number here doesn't mean that there isn't one. This isn't 0, this is a 1. We just have gotten into the habit of not writing out ones because it's just assumed that there is 1 mole there. So anytime you don't see a number, you just think of it as being a 1. Here's what the mole ratio is going to look like. Once you have a balanced equation, and this is why you have to know how to balance equations, and you have to know how to balance equations that are properly written as far as their formulas are concerned. So not only do you have to know what the coefficients are, but you have to make sure that the subscripts on each of the atoms are correct also. So once you have one of those, we can figure out what the molar ratio is between any 2 things in the balanced equation. So if I ask what the molar ratio is between hydrogen and ammonia, then all I have to do is look at the coefficients of the balanced reaction. And for hydrogen, it's going to be 3, and for ammonia, it's going to be 2. So when I say, what is the molar ratio between hydrogen and ammonia? The answer is 3 moles of H2. Okay, it's not just 3, but it has to have units with it as well. And 2 moles of NH3. So notice I'm just taking the coefficients from the balanced equation and I'm sticking them into a ratio. Which one goes on the bottom and which one goes on top will depend on your problem. And it'll depend on what you have to cancel out. And we'll see what that looks like when we actually get to a sample problem. So just to look at all of the other molar ratios that we can generate from just this one equation, the one between nitrogen and hydrogen will be 1 mole of nitrogen, because remember we said that nitrogen, even though it doesn't have a number in front of it, is actually 1 mole of nitrogen, and then 3 moles of hydrogen comes from the coefficient of hydrogen. And then what's the molar ratio between N2 finally and ammonia? And by this time you're starting to get the point, is that it's going to be 1 mole of nitrogen divided by 2 moles of ammonia. So now next we're going to see how the molar ratio is the key, is the center of all of stoichiometry. And it is one thing that's going to be visible and used in every single stoichiometry problem.